Welcome back to Physical Science 20. This is the last section in the PW2 section. So PW2.5 Curved Mirror Reflection Part 2. So Part 1, we dealt with sketching the diagrams and figuring out various results that apply to concave and convex mirrors. Now we'll look at a mathematical way. So apply the laws of reflection using the magnification equation and the curved mirror equation to solve problems. So I'm not going to go over the derivation of that, but we are going to use them and apply them. So the mathematical method of locating the image, the spherical mirror model can be used to develop a simple equation for spherical mirrors. You must use the periaxial array method, which states that only rays that are close to and almost parallel to the principal axis are used to form an image. Using this in combination with the law of reflection leads to the mirror equation relating focal length, image position, and object position, and it's right there. So using this equation, we're assuming that we don't have a mirror that's made such that spherical aberration will occur. We're using a mirror that hopefully reflects things to the right areas. So it gives us a good result. Magnification, another property of spherical mirror is magnification, which is how smaller or how larger the image is compared to the object. In practice, this is a simple ratio. So basically, yes, it's a ratio for image height to object height. And if we looked at similar triangle geometry, we could see that that works for distance as well. So here it is right here. So we can either relate image height to object height, or we can use distance of image to distance of object, and we have a negative sign inserted there, and we'll see why when we go through a bunch of examples, because the negative tells us whether it's inverted or upright. Image position is positive for a real image because it's on the left-hand side of the mirror. When using the preceding equations, thus the magnification is negative, which means that it's going to be inverted. So if we get a negative magnification, if M is negative, that means it's inverted compared to the object. If the object is beyond C, if I take the absolute value of the magnification, its image is going to be less than 1. This means that the image is smaller. If the object is placed in between C and F, as we've seen earlier, and if I were to take the absolute value of the magnification for the real image, it's going to be greater than 1. Thus, the image is larger than the object. Okay, well, so what we'll do is we'll go through two examples. We'll go through a concave example, and then we'll go through a convex example to see how this all comes together. So a concave mirror has a radius of 20 centimeters. So what that means is that this is 20. So hey, we can figure out what F is, right? Because F is equal to the radius divided by 2. So we know that the focal length is 10 centimeters because the focal length is half of this. Now C here, of course, represents the center of the sphere. If we were to extend this concave mirror all the way around, it'd be the center of the mirror. So from C to right here, this vertex, or where it hits the mirror, that's really radius. And if I take half that radius, I get the focal point. So here, looking at image position, magnification, etc. So we know focal length is 10. A 2 centimeter tall object. So we know the height of the object. Object height. And it's placed 30 centimeters from the mirror. So we know dou. So anything on this side is considered the positive area. Anything behind here is considered the negative area. So I know F, I know dou. So what I can do here is I can use the mirror equation to figure out the image distance or the image position. So 1 over 10 equals 1 over dou plus 1 over di. Okay. 1 divided by 10, 0.1. 1 divided by 30, type in your calculator, decimal 0.3 repeating. Okay. So to get die, I say we have to isolate 1 over die first of all. So that means subtracting this from each side. And don't just round that off to 0.03. Actually type in 3 a bunch of times in your calculator. So we'll get 0.06 repeating. Now the easiest way to solve for die here is to simply do this manipulation, because as you know that if I multiply each side by die and then divide by 0.06, I get the same result. So I get that, and that'll work out to be 15. I'll go 2 decimal places for the measurement there. 15 centimeters. So what that means, if my as you can see here, my object was beyond where C is. So my C value was 20, but the object is beyond there. And of course, we looked at in the last section, when I have an object that's beyond C, the image is going to be in between C and F somewhere. It's also going to be inverted and smaller. So according to this, it's going to be 15 centimeters away, which is reasonable. That's going to be in between F and C, 10 and 20. It's at 15. Image magnification. Now I could use a couple of different things. I could use image. I don't know image height yet, so I'm going to have to figure that out. But for magnification, again, one way I can do it is negative die over dou. So my image distance I figured out was 15, but I'm going to take the negative of that because that's what the formula suggests, over 30, and I get negative 0.5 times as large, because it's a ratio, right? So it's how many times bigger. So I know it's half as big, and you can look at that. This does look half as big as that. And of course, the negative sign means image is inverted. So that means it's on the opposite side. So yes, if HO is pointing upwards, HI is pointing downwards. If HO was down here, HI would be the opposite. And lastly, C, the image height. Of course, we can use it by using that magnification formula. We had M is equal to HI over HO, which equals negative die over dou. So we could just use that part there to figure out what HI is. So height of object, we were told, is 2 centimeters. And the image distance, we were told, was 15. I'm going to take the negative of that. And the object distance was 30. So, of course, here, to get HI by itself, multiply by 2. Multiply by 2. So we get that. And HI works out to negative 15 times 2 divided by 30 equals negative 1.0. So the image height, and of course if I get a negative for an image height, that also means image is inverted, just like over here. So that's what the negative means. The negative just simply means that the image is going to be inverted compared to the object. So that's how you do that. So what we'll do is we'll come back, and in the next video we'll look at how this applies to a convex mirror.